Hello guys, am I audible? Can you let me know in chat or fire thumbs up whether okay, nice, I'm audible. Mhm. Uh, so I guess since a few of you have joined already, so I guess we can start the meeting. So, so hello everyone. So I'm Lakshya Sagi, your discrete math problem solving TA, and this is the I guess seventh problem solving session. So today we'll be talking more about graphs, chromatic number of graphs, Hamiltonian paths, and stuff like that. So basically the content which you have seen over the lecture videos this week. So we'll start with the problems for today, I guess. So let me just share my screen, guys. So today you might see a bit technical glitches or something like that between the meeting. My laptop is like, somewhat glitchy today, so I apologize in advance if something happens. Um, so is my screen visible, guys? The Google Docs which I'm sharing right now. Can you give a thumbs up or like Aditya? Can you type in chat while? Okay, sure. Thanks. So my screen is visible. So I guess we'll just start right away with the problems. So today, problems I don't think will be much hard because you guys have already seen this kind of stuff. So let's just get into it. So first question is, basically let k, m, comma n represent a complete bipartite graph where m and n are positive integers. What is the chromatic number of this graph? So first of all, let us make the notation a bit clear. So I'll just type out the notation before starting everything. So what does km comma n mean? I'm sure this must have been covered in the lectures, but just to remind you guys, so that km comma n means uh, complete bipartite graph. So bipartite graph, I assume you know what is bipartite graph and what is a complete bipartite graph. Basically, every possible edge between the two sides is there in the graph. So a complete bipartite graph with m vertices on one side and n on the other. So this is km comma n, and similarly, like this notation I covered in last session also, but I'll just write it down again. So kn means complete graph on this vertices. So note that m comma n means basically complete bipartite graph. So a bipartition of vertices m with m vertices on one side and n on the other. Whereas a kn means that you have, okay, why did I turn off caps lock? Whereas kn means basically you just have n vertices and you join every possible pair with an edge. So I hope the difference between kn and kn comma n is clear. So some more maybe I'll just write down these two notations for now and we'll update this if the other notations. HSC, so Km common is a complete bipartite graph with m vertices on one side and n on the other. Now we need to know what is the chromatic number of this graph. So chromatic number again is reminding you guys, chromatic number is minimum number of, so coloring you must have seen in these week lecture what how what is basically coloring of a graph, what is a vertex coloring of a graph. So chromatic number is just the minimum possible colors required so that the graph can be like minimum number of colors required so that the vertex coloring can exist. Minimum number of colors required for a valid vertex coloring to exist. So I hope this definition is clear to you guys. What is a valid vertex coloring? A valid vertex coloring is a coloring in which for every edge in the graph, the two vertices of that edge have different colors. So now so basically, if we very basic coloring would be we could just color every vertex with a different color. Then what can happen is between every possible edge, or both all the endpoints will have different colors. So we need to find like n is a trivial bound on the chromatic number, like number of vertices, since we can just color every vertex with a different color. But we need to find chromatic number is generally referred to as the minimum number of colors required for a valid vertex coloring. So like in this km comma n, we can just see like if we have like m plus n colors, we can easily color. We can easily have a valid coloring, just color every vertex differently. But we'll try to find out the minimum number of colors needed. So note that you need to show whenever you need to show like something has chromatic number x, then you need to show that you can color the vertices using these x colors. And also another thing you need to show is that you cannot color the vertices using x minus 1 colors. That's when it would be the minimum number of colors needed. So I hope my point makes sense. So my point is just that for to show something is a chromatic number. Let's say I show that I'll show that to show that suppose this has a chromatic number of 2. I need to show that using two colors I can have a valid coloring. I also need to show that using one color I will not have a valid coloring. So just making that clear to you guys. That's how we get the minimum part, that you need at least this much colors. So here, one thing to note is that our claim is, I guess this question is already straightforward. It's straightforward. Chromatic number is 2. So what I'm claiming is that the chromatic number for this graph would be 2. And I can just use two colors and color the vertices such that it is a valid coloring. So to show this, we'll first show. So there are two things we need to prove. So we need to show that uh, we can color the graph using two colors. We can color the vertices using two colors, and also we need to show that we cannot color using just one color. We cannot color the vertices. So like I just said that to show that this is the minimum number of colors required, since we need the minimum part for chromatic number. So we have to show two parts. So we need to show that we can color the vertices using two colors. So the chromatic number is 2. And we also need to show that we cannot color using like 2 minus 1, which is just one color. So I guess this part is trivial, that we cannot color the vertices using just one color, because if you just use one color, then every vertex will have the same color. So in that case, for any edge, its both endpoints will be having same color, so that won't be a valid coloring. So I guess this part is trivial. Because if you use just one color, then every vertex will be having the same color. So uh, even if there exists one edge, its both endpoints will have same color, and that's not a valid coloring. So I'll not write down what I just said since it's trivial. So the main part which we need to show is that we can color this graph using two colors, or maybe just the graph only. So we need to show that we can color the vertices of this km comma n graph using two colors, such that it's a valid coloring. So note that this km comma n is a complete bipartite graph. So any ideas, guys? I think it's fairly straightforward. So I believe you guys can answer this question. So can you guys? So basically, what I'm asking is, can you guys show that we can color this km comma n using just two colors? Maybe someone can try it out in chat. Okay, someone is typing. So maybe like Khushi is typing something. So while Khushi is typing, maybe I'll just start discussing this part. So basically, what we need to show is that we can color the graph using just two colors. To show this is not too difficult, since km comma n, like let's say maybe I'll just to show that km comma n can be colored using just two colors. Assume the colors to be like, let's say the colors are C1 and C2. So now what we can do is, oh yeah, Khushi is writing in the chat, and Khushi, what you have written is correct. I'll just uh, say the same thing over here. So to show, so basically we need to show that km comment can be colored using just two colors. We'll assume the two colors to be C1 and C2. So now since it is a bipartite graph, what's the property for bipartite graph? That since km comma n is bipartite, uh, the vertices, basically the left side of vertices, the left side of. So what is a bipartite graph? Bipartite graph is a graph in which the vertices are uh, can be separated into two sides, let's say left and right side. So like left side has m vertices and right side has n vertices, such that all the edges are present just between these left and right sides. Like no edges present between just left side vertices and no edges present between right side vertices of the right side. So that's the definition of bipartite graph. It's so basically the left side of vertices. Let's say we color all the left side of vertices with color with C1 and right side with C2. So I'm just saying, so to show that using two colors I can color the vertices, I'll just show that a coloring exists uh, using these two colors. A valid coloring exists using just two colors. So what is that valid coloring? Just color the since km comment is bipartite, it will have left side as well as a right side, and no edges will be present between vertices of left side, and similarly no edges will be present between the vertices of right side. So we just color the left side of vertices with C1 and right side with C2. So does everyone now see that it's a valid coloring? Since every edge is between, since every edge in km comma n, okay, sorry, since every edge in km comma n is between left and right side, and every edge has endpoints as. So basically, every edge has one vertex from left side and other vertex from right side. So every edge will have C1 vertex. The left side vertex will have C1 color, and right side will be basically C2 color. So uh, that's the definition for a valid coloring, right? That every edge, the endpoints of every edge should have different colors. And what we have just shown here is that if we just color left side with C1 and right side with C2, now in every edge will be between left and right side only, since it's a bipartite graph. So every edge will have one endpoint from C1, which one endpoint from left side, which will be colored C1, and one from right side, which will be colored as C2. So uh, hence this is a valid coloring, and endpoints of every edge have different colors. So yeah, that's exactly what Khushi said in the chat also. Uh, this is what I'm saying also, that there are two sides of a paragraph, left side and right side. Just color left side with color 1 and right side with color 2. So now every edge will have one endpoint as color 1 and other endpoint as color 2. So it's easy because now, so this is, so again, this was just one part of the solution, that we showed that using two colors we were able to obtain a valid coloring. To show that this is the minimum possible number of colors needed, we'll also need to show that using one color we cannot have a valid coloring. So that part was trivial, as say if we just have one color, then every vertex will be colored with the same color, and so for every edge the both endpoints will be having just the same color, which will be like not a valid coloring. So I hope it's clear to you guys. So moving on, let's come to second question. So this was a basic introduction to coloring. I guess it was not too difficult, this question, but nonetheless I just tried to cover it. So now let's come to the second question. So second question is again similar in favor to the first one. It's a bit easier, I think. So second question is just asking, what is the number of colors required to color a complete graph containing n vertices? So suppose we have a complete graph. Basically, what we have is kn. That a complete and on n vertices we have kn. So that like there exists an edge between every pair of vertices. So here, what do you think, guys? What will be the minimum number of color needed? I'll just say minimum also. So, guys, can anyone type in chat? What do you think will be the chromatic number in the case of Kn? What will the minimum number of colors required to color a complete graph containing n vertices? Okay. Aditya is writing n. Khushi is writing 5. Okay. And yes, Khushi has changed her answer to n, and yeah, that's the correct answer. So we'll be needing n colors here. I think Khushi, you were confused with the planar graphs, because planar graphs have a property that all planar graphs can be covered using 5 colors. But for general graphs, you there are cases where you will need to have n colors. So basically, in Kn, in this complete graph containing n vertices, we'll need n colors. And so, like I argued earlier also, uh, that to show that using like I argued earlier that every graph can be colored using n colors. Like there exists a valid coloring using n colors for every graph. So so for this kn also a valid coloring will exist using n colors. But the second point which we need to show is that this is the minimum number of colors required. So yeah, Aditya has written the argument in chat, while this will be n, the answer will be n here. And yes, Aditya, your argument is correct. I'll just say it out loud also for everyone. So just reminding you guys, so just copying the copying the above part So now what we need to show is that, just to remind you guys, what do we need to show to say that n colors are needed? We need to show that we can color the graph using n colors, and this part is actually trivial here, since every vertex trivial, as every vertex will have different color, a different color. So using n colors, it's trivial that we can color, we can have a valid coloring, but we also need to show like why is this the minimum number of colors required in this complete graph. So here, in this first question, the trickier part was to show the coloring using just two colors, but showing that this was the minimum, it was not too difficult, because the claim was it cannot be colored using one color. Here in the second question, the roles have reversed. Here using here having a valid coloring using n colors, this part is trivial, but the part where we need to show that this is the minimum possible, that part will require some sort of proof. So to show that we need at least n colors, we need so now we need to show that we need at least n colors. So for this, we'll need to show that we cannot color the using we cannot color using n minus 1 colors, and this part here won't be trivial. I hope it's clear to you guys what I am saying. So first, we have shown that we can color the graph using n colors, as every vertex will have a different color. Now to show that this is the minimum number of colors required, we'll need to show that we need at least n colors. So for showing this part, we'll just show that we cannot color the graph using n minus 1 colors here. Or maybe, yeah, here the graph is kn, basically, the complete graph containing n vertices. So to show this part, to show that kn can't be colored using n minus 1 colors, so Aditya has written that as all vertices of a complete graph are adjacent to each other, therefore chromatic number will be same as number of vertices. Yeah, I'll just formalize your the statement which you have written. Your statement is correct, but I'll just formalize it a bit here. So now what we need to show is that kn can't be colored using n vertices. To show that kn can't be colored using n minus 1 color, we use contradiction, let's say. So we'll use contradiction. The basis of contradiction is that, to show that kn can't be colored using n minus 1 colors, we'll assume that it can be colored, and then we'll obtain some bogus result, and then we can say that. So let's assume that kn can be colored using n minus 1 colors. So if kn can be colored using n minus 1 colors, now we have already studied, you guys have already studied pigeonhole principle, right? So what do we have? There will be a similar sort of pigeonhole principle argument required here also. I'll just say it out loud. So as there are n vertices, we have n vertices in the graph, but only n minus 1 colors, since we have assumed that we can color using n minus 1 colors only. So what we'll having in the graph, we'll have that there are n vertices, but only n minus 1 colors. So by pigeonhole principle, there will exist at least at least one color which will be given to, okay, maybe I just said, there will exist a color which will be given to two vertices. So I hope this claim is clear using pigeonhole principle. Since let's just assume, like in the pigeonhole principle, pigeons sit in the holes, and every pigeon can go to one hole only. So similarly here, what we are doing is every vertices are the pigeons here, sort of, because every vertex can be assigned to only one color, but one color can be assigned to multiple vertices. So colors correspond to, if you have attended the previous sessions, I gave a sort of a, I don't know, parallel, or I just gave us, I told you guys how to interpret this pigeon principal argument. So here what we can see is that vertices can be thought of as pigeons and holes can be thought of as the colors. So there are n pigeons but only n minus 1 holes. So there will exist a hole which will contain, which will have at least 2 pigeons. So similarly here we'll say that there will exist a color which will be given to at least 2 vertices. So let's say the vertices are v1 and v2. Let's say the vertices are v1 and v2. But so what we have say, said till now is that for visual principle there will exist a color which will be given to 2 vertices. So these 2 vertices which have the same color. So let's say the vertices which have the same color are v1 and v2. So I first showed that there will exist a color which will be given to at least 2 vertices. So we have at least 2 vertices which have the same color. So let's say these are the vertices v1 and v2. So, but since Kn is a complete graph, but since our graph is a complete graph, there will exist an edge between v1 comma v2. So our graph was a complete graph, as the question says that we are dealing with a complete graph. So what is a complete graph? Every pair of vertices will have an edge between them. So v1 and v2 will have an edge between them. But what we had said earlier, that v1 and v2 have the same color. But also we are saying that v1 and v2, so what we have said is v1 and v2 are of the same color. Also we have said that there will be an edge between v1 and v2, but for a coloring to be valid, uh, all the endpoints of every edge should have different colors. So I hope you guys see the contradiction here. Basically we have devised a contradiction here, that this edge v1 comma v2 will have both the endpoints as the same color, which can't be the case, as it's a valid, as we had assumed that this is a valid coloring. So I'll just type it down also. Since the graphically hence our coloring is not a valid coloring, since uh, all the endpoints or all the edges should have different colors as endpoints in a valid coloring. So this is a contradiction, and this is a contradiction. So for showing contradiction, we assume that Kn can be colored using n minus 1 colors. So what we have shown is that this statement is, so we assume that Kn can be colored using n minus 1 colors. Then we showed that this is not possible as we obtain a contradiction. So what we assumed initially is false. So the correct statement would be Kn, Kn can't be colored with n minus 1 color. So if it can't be colored using n minus 1 colors, it will require at least n colors. This part only shows that it will require at least n colors, and we had initially argued that we can use exactly n colors. Uh, we can use exactly n colors and have a valid coloring. So the chromatic number will then be n only in this case. So I hope this argument is clear to you guys. So if you have any doubt, you can ask in chat. Otherwise, I'll move on to the next question. going down to the very basic principle again. It's nothing too fancy, but I'll just repeat it because this is the same formula, same approach which will use whenever you prove something of like solving of a minima, or like let's say from little chromatic number. So what we will need to show every time is that the solution which we obtain is a valid solution, and then we'll also need to show that this is the minimum possible valid solution. So for that, let's say our solution was x, so we need to show that x is valid. We'll also need to show that x minus 1 is not valid. Only in that case we can say that this is the minimum valid solution. I hope it's clear to you guys. So yeah, the second question is done. Now let's come to third question. Now this question is a bit easy. So which of the following graphs, it's MCQ based question, so which of the following graphs is planar? So if you guys want, you can answer in chat also. In the meantime, I'll also press now. So option A, so we'll just go option by option to see which graph is planar and which is not planar. So we have all, you guys must have already seen in lecture that K5 and K3, 3 are not planar. This is not too difficult to prove also using Euler's identity or stuff like that. We can easily prove that these two are not planar. So not planar. Discussed in the so one thing is that for planarity, for these two graphs at least, like K5 and K33 are a very just take my word for it now that K5 and K3, 3, these two graphs are very important in terms of planarity. There are lots of theorems regarding these two graphs by which you can show whether any general graph is planar or not. So you'll just have to maybe just remember that these two graphs are very important in terms of planarity. So always just remember that these two graphs are all non-planar. This advice I'll give you, that always remember that K5 and K3, 3 are non-planar, and you can derive planarity or non-planarity for any other graph using only these two graphs. But that's a story for another time. For now, I'll just say that remember these two graphs are non-planar. Non-planar. So now we have option C. Option C is K6. So K5 is a complete graph on 5 vertices. And okay, Tehseen, you have written option. Maybe I'll just come to your argument later. So what is K6, guys? K5 was a complete graph on 5 vertices, and K6 is a complete graph on 6 vertices. So if the even if the like the 5 vertices, a complete graph of 5 vertices was non-planar, first of all. So K6 will have K5 as a subgraph, right? So you take from this K6, you take any 5 vertices and they'll form a K5 component, right? So K5 will, some component of this K6 will be non-planar. So this overall K6 will also be non-planar. Does my argument make sense, guys? What I'm saying is that K6 is a bigger graph than K5 already. Like K6 already contains K5. And if K5 was itself non-planar, how can K6 be planar? You can just prove this using contradiction also. Like let's assume that K6 was planar. Then after deleting some edges from K6, then again the graph should be planar. And after deleting some edges, we can obtain K5 from K6. So if K6 was planar, then K5 was also planar. But since we already know that K5 is not planar, so K6 won't be planar. Maybe you guys can listen to what I said in the recording. I'll just type it down also. Not planar. K5 is not planar, and K6 is just a superset of K5. Basically, K6 contains K5. So If it contains something which is non-planar, how can the bigger thing be planar? We have these three options are not planar, and option D is K4. So K4 is actually planar. I'll just show you guys a figure how it is planar. Like, uh, so how is it K4 is planar? I'll just share an image with you guys. So K4 is just a complete graph on N4 vertices. So to show something is planar, we just need to show a planar, an embedding of that thing on a plane, right? So we just need to show how can we have K4 graph on a plane. So we can have K4 on a plane in this manner. Okay, taking guys. I think there are some technical issues. I'm not able to copy. Yeah, now I'm. Let's just have it at that. So this is the K4 graph, right, guys? Uh, this highlight graph is the K4. You can see that there are 4 vertices and there is an edge between every possible pair. And you can see this is a planar embedding for K4. Like there are 6 edges in K4. These are the 6 edges, and all the edges are lying in the plane itself and are non-intersecting. So K4 is planar. As it can be embedded in a plane as shown. So for this option, so this option D, you can see this this is the planar embedding for K4. So that's why K4 is planar. So option D is the correct answer. I'll look in the line the correct answer. Or maybe I'll just not here. So I can't answer. So ABC we already showed that this was not planar, and to check whether K4 is and the option D K4 is planar or not, we have just shown that there exists a planar embedding for K4. These are the 4 vertices and these edges are embedded in a plane. So K4 is obviously planar, and we have a planar embedding for that. So I guess it was. I guess this is okay. So Tehseen, you had written in chat option A for this question. So is it clear to you why option A won't be the case? Actually, the question is which of the following graph is planar, and it was already discussed in the lecture that like option A is K5, K5 is not planar. This has already been discussed in the lecture, right? And you should remember like this K5 and K3, 3 are very important graphs in context of planarity. These two you should always remember that they are not planar. Okay, it's clear to you. Nice. So let's come to the first question then, guys. First question asks how many edges are there in the complement of P6? So complement, I guess you already know what is complement of a graph. Complement of a graph is a graph in which you just have the edges which are not present in the original graph, like over the same vertex set. So first of all, okay, the question is how many edges are there in complement of P6? What is this notation P6? P6 just denotes a graph which is a straightforward path on 6 vertices. So I'll just add this to the notation also. What does Pn mean? So Pn means uh, path Pn is a graph which is just a path of n vertices. So Pn is a graph which has n vertices and only like n minus one edges. It's sort of a linked list, you can assume. If you already know what is a linked list, so Pn is just a linked list on n vertices. So it will have n minus one edges. So that's the definition of Pn. So now coming to this. So how many edges are there in complement of P6? So we have like total possible number of edges in graph of n vertices is NC2. Right guys, so I'll just take this instead of P6, I'll just say for Pn, like how many edges are there in the complement of Pn. I'll just answer that question and you can just plug in the value of n as 6 later. So the question asks how many edges are there in complement of Pn. So first of all, what is the complement? I guess it has already been covered in the lectures and I said again. So in a complement of a graph, what you do is you just add every edge which is not in the original graph and you delete the edges which are in the original graph. So like a graph on the same, a graph which just contains the edges which are not present in the original graph. That's the complement graph. I don't think the definition is too difficult to understand. So total number of edges which in a graph of n vertices, there will be total NC2 possible number of edges, right? Because there are NC2 possible pairs which we can choose. So now what we can say is that a graph. So a path graph is just a graph with on n vertices, which is just a path, basically a linked list on n vertices. So it will just have n minus one edges, right? Because like a graph which has like vertices v1, v2, v3 up to vn, it will just have n minus one edges which are from like v1 to v2, then v2, v3, then v3, v4 up to vn minus one comma vn. A graph pn will have n minus one. So I hope it's clear. So total number of edges present in so these are so NC2 is the over a graph of n vertices, all the possible number of edges which can be present in a graph on n vertices. And we have in our graph Pn, we just have these n minus one edges. So the edges which are not present in Pn would be just the difference of these two quantities, right? Because these are the total possible edges and these are the edges which are actually present. So the edges which are not present would be the difference of these two. So it would be just NC2 minus of n minus 1. Basically, total edges minus the edges present. Maybe I'll just write it that way also. Total edges minus present edges. And this will evaluate to this thing, like NC2 minus of n minus 1. Maybe yes, something like this. Total edges minus present edges and the 17 single line. So this will be the formula for like total number of edges not present in Pn, and actually this is actually the edges which are not present in Pn will be the edges which will be present in complement of Pn, right? So this will be equal to number of edges in complement. So edges present in complement of Pn will just be this quantity. So for P6, so just putting, so I have evaluated this. I hope it's clear to you guys how I arrived at this expression. So how I arrived at this, just took the total number of edges and reduce the edges which are actually present from that amount. So now if I put n equals to 6, since we have P6 graph, so we get number of edges in complement of P6 equals, just put n equals 6 here. So we'll have 62 minus of 6 minus 1, which is 5. So that will evaluate to 62 evaluates to 6 times 5 minus by 2, which will be 15. 15 minus 5, which will be 10. You guys can do the math by yourself. You'll arrive at this answer. So we'll just get, like, putting n equals 6 here, we'll just get 10. So Aditya and Tehsin, you have written 10 edges. So yeah, that's the correct answer. So for any general end, let's say it was not 6, and any general end, you just have this general formula nc2 minus of n minus 1, which is not too hard to derive either. I just thought it would be simpler if I just did was general end rather than specific. Now coming to sixth question. So sixth question is asking us the chromatic number of the hypercube Q3. So you don't need to necessarily know what is a hypercube. So just assume like you have been given this graph, this AB, this graph as shown in the figure, and you just have to tell what would be the chromatic number for this graph. So would anyone like to answer, like, what would be the chromatic number for this? Maybe you guys can try. How can we, like, color this in the minimum possible manner to have a valid coloring? Okay, so this, maybe you guys can try it out in chat. I'll give you a minute or two. After that, I'll discuss this. Basically, don't need to show, like, minimum, just answer what comes to your mind, like a way in which you can color, which you think is correct. Okay, so Aditya has written 4 and Khushi has written 2. So I'll first start with Khushi. So Khushi, how did you arrive at 2? So Khushi, can you answer? Can you type in chat? Why did you arrive at 2? Because Aditya, you have written 4. So if Khushi is able to, maybe your solution is also correct, Aditya. But if someone is able to answer in less than like 4, like let's say Khushi was able to explain how she colored using just 2 colors, then it's a better solution, right? Because we need the minimum number of colors. So Khushi, how did you arrive at 2? Can you answer? Okay, Aditya is saying color of A and D can be same, and so diagonal. So here we see, like, in the outer cycle ABCD. Aditya is saying since this is a cycle, so A and B can't have the same color as they are connected by an. So only A and C can't have the same color. So maybe A and D can have the same color. and B and C can have the same color, but these two colors should be different. So let's say the colors were something like red and blue. So suppose I color A and D with red and B and C with blue. Then Aditya, you are repeating the same argument in the internal structure that the colors for E and H should be same and G and F should be same, but these two colors should be different. So that's how you are arriving at 4, right? Okay, Kushi has written every vertex has 3 degrees, so total number of vertices is 8. So so Kushi, generally for coloring, you just need to like you have said that your answer you can color using two colors. So you need to show actually like what is the coloring. How can you color these vertices using two colors? Actually, your answer of two is correct. So Aditya, now I'll show you guys how to arrive it at that answer. So Aditya is on the right track. So Aditya has arrived at 4, but he's on the right track to get to 2. So what Aditya is saying? Aditya is saying that there is an outer cycle and there is an inner cycle. So in the outer cycle, A and D can have the same color, B and C can have the same color. Similarly, in inner cycle, G and F can have the same color, and E and H can have the same color. So if they're dividing it into 4 groups, he's saying, let's say we allot one color to A and D, another color to B and C, third color to E and H, and fourth color to G and F. That's a first approach. But note, Aditya, that in that approach, one thing which you can improve on, like how can you come from 4 to 2, what you can improve on is the fact that uh, G and F need to have the same color, but that color need not be different from the color allotted to A and D. Since like A, G, F, and D don't share any edge, so maybe instead of coloring G and F as a color different from A and D's color, you can just have these two also of the same color as A and D. And similarly for E and H also. For E and H, we can give the same color as B and C. Tessin, can you explain what were you asking? How is it same color? In the meanwhile, I'll just write down the answer for you guys. So I hope the idea is clear. Aditya's idea was that maybe we can have A and D of the same color since they don't share an edge, and B and C of the same color. And similarly, G and F can be same color, E and H can be same color. Now what I'm saying is maybe we can also have A, G, F, and D all of the same color. Instead of just A and D, I just have all these 4 as the same color. And similarly, I have all these 4 as the same color. So I'll just write it down also. So to show basically that this is a valid, to show something is a valid coloring, uh, or like let's just say to show that the chromatic number is 2, we need to show that. I'll just write down the answer. Answer is chromatic number is 2. So we need to show that is the minimum possible number. So for this we need to show that we cannot color using just one color, which is trivial. And now we need to show how can we color it using two colors actually. So how can we color it using two colors? Let the colors be C1 and C2. Then we color the set. We color the set of vertices A, comma D. Basically these opposite ends of the cycle, and then these opposite ends of the cycle which don't share an edge with A and D. So G and F. So we color the set ADGF with C1, and the other set, let's just write down. So it would be BCEH with C2. So as we can see, so how I have color this A, G, F, and D. All these 4 have the same color. Then this B, E, H, C have the same color. And as we can see, there is no common edge. This no edge between vertices of the same color. Like there is no edge between AD, DG, GF, or AG, or DF, or AF. Right? So there is no edge between any of these two vertices, and similarly no edge between any of these two vertices. So using these two colors, I am able to obtain a valid coloring. So can we easily see that this is a valid coloring? I hope it's clear to you guys. It's too difficult to see. So the trick was just like identifying first of all what Aditya identified that A and D can have same color, and then also identifying the fact that the colors of these endpoints need not be different from the colors of these outer endpoints. So yeah. So now coming to next question. So next two questions are just true and false. So it's quite easy. So Kushi is asking. So A is connected to ECB. So if A has C1 colors, these three. So Kushi is giving the argument, a similar thinking argument. So Kushi is saying just in the previous question that A is connected to ECB. So ECB can be given, let's say, a color C2, and A is given a color C1. Then D also has a C1 color, and H has C2 color. So yeah, Khushi, basically what you are arguing in your, like what you have written in this, in your message is just the same thing which I have written here, right? Which I have written in the solution. I've just made these sets only. That A, D, G, and F will have color C1, and the other set will have C2 color. So I guess like you can write the same thing in different types, in different ways basically. So yeah, I guess this is just the answer. Just underline this. So now coming back to sixth question. Sixth question is saying K22 is isomorphic to C4. Is this statement true or false? So first of all, I hope you guys know what is isomorphic, right? So isomorphic graph, like let's say you have to show that G1 is graph G1 is isomorphic to G2. So the one way to like informally think of what is isomorphic is that that they if G1 is isomorphic to G2, then G1 and G2 are just the same graphs but have different labelings or vertices. So maybe this has been covered in the lectures also, so I'm not going to emphasize on the definition of isomorphic graph so much, but just to give you an intuition like what is isomorphic graph. So two graphs are isomorphic if they are actually the same graph but have different labeling for vertices. Like if I change the labeling of one graph in some manner, then we can obtain the second graph. Exactly. So not too like complicated or anything. So yeah, just leave it at that. So K22 is isomorphic to C4. So what do you guys think? Is this statement true or false? Yeah. So Kushi is writing in the chat that this statement is true. That K22 is isomorphic to C4. So yeah, Kushi, your answer is right. That this statement is true. I'll just show you guys the figure why is it true. So let's just uh, have the figure for K22 first. Okay. That's a pretty big figure. So this is, let's say guys, K22 graph, right? And now I have another graph, which is C4. I'm just showing the two diagrams to you guys so you can compare by yourself if these two are similar to each other or not. So you guys, you can see these are the two graphs which we have. This is like K to 2 graph. K to 2 is just like a bipartite graph which has two edges on both sides. So here, and all the edges are connected. Okay. Yeah. So okay, here K to 2 is basically this is what I've shown is this is not from left to right. Say maybe 1 second, guys. I'll just see. So here what we are seeing, this K to 2 graph is actually not divided. The bipartite graph is not from like left to right side, but from top to bottom side. The figure has come in rotated manner, sorry. So you can easily see that the top is one side of the bipartite graph and bottom is one side of the bipartite graph here. Because like there are no edges between these two top vertices and similarly no edges between these two bottom vertices, right? And this is the C4 graph. C4 is nothing but just a cycle on four vertices. So what we need to show actually is that if this statement is true, then these two are actually of the same shape. So I hope you guys can see how these are isomorphic. So maybe to just give an intuition, I will just say to you guys. Let's just say we start from this vertex. That K22 is similar to C4. Let's just start with from this vertex. Then if I go to this vertex, then this vertex, then this vertex, then back to the original vertex. Basically, I've obtained a cycle of four. So it's something similar to like this C4 graph. Or if you want to see more properly, let's just take this C2 graph, this C4 graph of V1, V2, V3, and V4, and take like V1 and V4 on one side. Let's just say these are V1 and V4. These are the vertices. Let's say this vertex, this top vertex of this K2 was V1, and this was V4. And similarly, this was V2, this vertex was V2, and this vertex was V3. Then I think it's not too difficult to see that these are actually the same graph, because then since this vertex was V1 and this was V4, this edge just denotes V1 to V3 edge, and this denotes V2 to V4 edge, and you guys can work it out. So I hope it's not too difficult to see. So, I can see easily from the two graphs. So, yeah, so yeah, K22 is indeed isomorphic to C4. Well, this is line 2. Yeah, that is the correct answer. Yeah, so Aditya and Khushi, you had written true. So yeah, your answer was correct. This statement is indeed. So now let's come to seventh question. So seventh question is asking which of the following graphs is not Hamiltonian. So what are Hamiltonian graphs? So just serving a reminder to you guys of the definition. Hamiltonian graph. A graph which contains a path, or basically a graph which has a path containing all n minus 1 vertices. So a Hamiltonian path is a path which contains all the n minus 1 vertices. So a Hamiltonian graph is a graph which contains a Hamiltonian path. And what is a Hamiltonian path? A Hamiltonian path is a path which contains all the vertices of that graph. So that's a straightforward definition for the Hamiltonian graph. So the question is asking which of the following graphs is not Hamiltonian. So we'll just go through option by option. And also, I believe, okay, I just got rid option by option. So, what do you guys think? Is Kn Hamiltonian or not Hamiltonian? So we'll just go option by option whether which of the graphs are Hamiltonian, which of the following graphs are not Hamiltonian. Okay, maybe I'll just say two results which have been discussed in the lectures also. Like there is a theorem, right? Dirac's theorem or something, which says that if every vertex, this is, I'm just serving this as a reminder to you guys. This Dirac's theorem is already in the lecture, so it's not something new which I'm discussing. You can see some lectures also that if every vertex has degree greater than equals to n by 2, then the graph is Hamiltonian. So this is the statement of Dirac's theorem. So I'm not discussing its proof or anything. I'm just stating the same as has been discussed in the lectures. And similarly, there is also a theorem. Uh, I'm just stating these both of these theorems because, like, whenever you need to check for, like, generally when you need to check whether the graph is Hamiltonian or not, these two theorems are pretty useful. So, but note that one thing to note is that what this, like, Dirac's theorem, what it says is that if every vertex has degree greater than equal to n by 2, then the graph is Hamiltonian. But it's not a if and only if implication, like it's just a forward implication. So a graph can be Hamiltonian even if every vertex does not have a degree greater than n by 2. Like what this statement says is that if this claim is true, that every graph has degree greater than equal to n by 2, then the graph will be Hamiltonian. But suppose there exists a vertex which has degree less than n by 2, for that this statement does not claim anything, this theorem does not say anything. In that case, the graph can be Hamiltonian as well, or it can't be Hamiltonian. So it just says if this property holds, then this property holds. But it doesn't say anything about the other way around. Like a graph can be Hamiltonian even if this does not hold. So always be careful with the implications, guys. Like this is just a forward implication, not a forward as well as backward. Like not a if and only if, just a if statement. So similarly, another if statement. This was Or's theorem. So Or's theorem said that maybe I'll just copy its statement now. Maybe because uh, because like and directly copying the statement is easier than me writing it out. So okay, uh, maybe I could have written it down myself only. That would have been much better. But okay, this is what the fourth theorem claims, that if this statement is true, that degree of V plus degree of W for every pair of distinct non-adjoint vertices V and W of G. Just a second, guys. Sorry for it. Let's So this the Dirac theorem just said that if every vertex has degree n by 2, then the graph is Hamiltonian. And what O's theorem says is that if basically for every pair of non-distinct for every pair of distinct non-adjacent vertices V and W of G, basically any two pair of vertices which don't have an edge between them, if the sum of their degrees is greater than equal to n, then the graph is Hamiltonian. This is the O's theorem. This has also been covered in the lectures. So that's why I just copied its statement from like Wikipedia, because this is something which we have already seen in the lectures. I don't need to claim it formally. You guys must already know about this here, right? Yeah. So this is the Dirac theorem. This is also an if statement, not an if and only if statement. So there can be cases that where this statement fails, but the graph is still Hamiltonian. So coming back to the question at hand, these are just the two theorems regarding Hamiltonianity of a graph. So now coming to the question at hand. So what this question asks, which of the following graph is not Hamiltonian? So for Kn, so a graph Kn is a complete graph of on n vertices. So here we can see that for here every vertex of the graph will have a degree of n minus 1, right? In Kn, every graph of degree n, every vertex basically, every vertex will have a degree n, right? So what can we say then? Since every vertex will have a degree of n minus 1, will have a degree in k, and since there are like n vertices, so one vertex will have nh2 all the remaining n minus 1 vertices, so that every vertex will be having a degree of n minus 1. So and this is basically greater than equals to n by 2. Like we can assume that n is 2, n is greater than equal to 2, like the graph has at least 2 vertices. So in that case, we can see that this n minus 1 will always be greater than equal to n by 2. So we'll have a degree n minus 1, which is greater than equals n by 2. So here we can see that every vertex will then have a degree greater than equal to n by 2. So by Dirac's theorem, n is Hamiltonian. This is not too difficult to see. So option B, say, and then option B is Cn. So Cn is just a cycle on n vertices, and we need to find out whether this is a Hamiltonian graph or not a Hamiltonian graph. So I guess this is pretty straightforward to see that this a cycle on n vertices will be Hamiltonian, since we can just travel around the cycle to, like, let's say the cycle is from v1, v2, v3 up to vn, then we have a path which covers all the v1 to vn vertices. I hope it's clear to you guys. If it is not clear, you can ask in chat. I'll explain again. It is Hamiltonian as we can have a path containing all the vertices by going around on the cycle. So so Cn is just a cycle of n vertices. So when we move around the cycle, we'll be able to obtain. Maybe let's just take this example of cycle of 4 vertices. So we need a Hamiltonian path. So what will the Hamiltonian path here will be? It will be, we just start from v1 to v2, go v2 to v4, then v4 to v3, and we are done. So we just need to obtain a path which contains all the n vertices. So just take any edge and go from one endpoint to another endpoint. Like we can take this v2 comma v4 edge. So we'll just start at v2, go to v1, v3, then v4, and we are done. So that's how for every cycle of inverses is Hamiltonian. Now coming to option C. Option C is the graph K10, 9. So K10, 9 will be a complete bipartite graph which has 10 vertices on one side and 9 vertices on the other. And we need to find out whether it is Hamiltonian or not. So Aditya, you have written in the chat that option C is correct for this question. So you are claiming that this K10, 9 is not Hamiltonian. And why do you say so? Did you just by option of elimination? That was a guess because option A and B was actually Hamiltonian, so maybe option B. But you can see that it is also Hamiltonian. So the option actually is none of the correct answer is none of the above. So why is it Hamiltonian? So for this, for showing that K10, 9 is Hamiltonian, I'll use this O's theorem. Note that generally for checking Hamiltonian things, we have these two tools in mind, like Dirac's theorem and O's theorem. Here for Kn, I used directly Dirac's theorem, and I was able to say that Kn is Hamiltonian. For option B, I was able to just directly say without any theorem that is Hamiltonian. For option C, I'll be using Or's theorem. So it is Hamiltonian. And how can it be shown to be Hamiltonian? So this is a complete graph with 10 vertices on one side, 9 vertices on the other side. So consider any non-adjacent vertex pair P comma W. So if the vertex pair is non-adjacent, what I'm saying is, if V and W is non-adjacent in this, since this is a complete graph, complete bipartite graph, so this V and W should both lie either on left side, or both of them should lie on the right side. It cannot be the case that one of these lies in left side and other in right side, because in that case there will be an edge between V and W, as we have a complete bipartite graph. So as a bipartite graph, as the graph is complete bipartite, V and W, both V and W will either lie on the left side, or both will lie on the right side. It cannot be the case that one lies on left and other on right, as then they will be adjacent. So I hope this statement is clear to you guys. Like, graph is complete bipartite, so if one vertex is in left side and other is in right side, then there will exist an edge between those two vertices. It is by design, since the graph is complete bipartite graph. So either both V and W will lie on the left side of the graph, or both will lie on the right side of the graph, right? So till now only I claim this much thing. Now what can I say is, so what we needed to show actually was, like for O's theorem, what we need to show is that degree of V plus degree of W is greater than equals to n for every pair of distinct non-adjacent vertices. So we have shown till now that this V and W will lie either on left side or either on right side. Now I'll try to show that degree of V plus degree of W will be greater than equal to n also. So why will this be the case? So let's just take two cases. So let's assume V and W to be on right side, or maybe left side, on left side. So basically both are on the left side of the graph. So there are 9 vertices on the right side and 10 vertices on the left side. So every vertex on the left side will have 9 edges, right? 9 neighbors, because there are 9 vertices on the right side, and it's a complete bipartite graph. So both V and W will have edges to 9 of these 9 vertices which are lying on the right side. I hope it's clear to you guys what I'm saying. Let's assume V and W to be on the left side. So degree of V will be equals to degree of W, which will be equal to 9, since there are nine vertices on the right side. So both we will also have like 9 edges to the 9 vertices on the right side. Similarly, W will also have 9 edges to those 9 vertices, right? So then what we can say is that in this case, degree of V plus degree of W is equal to 9 plus 9, which is 18. And since the total number of vertices was Okay, I think I have made a mistake here, guys. Uh, Sorry, I meant to write it as k9 comma 9, and I wrote it as k10 comma 9 by mistake. So yeah, they just take it as k9 comma 9 instead, not k10 comma 9. My bad. So now what we have is like degree of v plus degree of w will be 9 plus 9, which is equals to 18, right? And what we have is total number of vertices. The total number of vertices is like left side contains 9 vertices, right side also contains 9 vertices. So total number of vertices is 18 also. So this is basically degree of v plus degree of w is greater than equals to n, as n equals 18. So in k9 comma 9 we know that there are 18 vertices, total number of vertices are 18. So we know that degree of v plus degree of w is greater than equals to 18, which is then greater than equals to n. So similarly, like we had assumed v and w to be on left side. Similarly, if v and w both are on right side, then also we can say that basically there will be 9 edges. Like degree of v and degree of 9 will again be degree of v and degree of w will again be 9. So again we can make the same claim in that case also. So then what we can say is like for any, so what we have shown is that for any non-adjacent v and w, degree of v plus degree of w will be greater than equals to n. So by fourth theorem, uh, a 9 comma 9 is Hamiltonian. I assume that v and w to be on left side. Similar argument can be done for right if both are on right side also. So what we have is degree of v is degree of w is 9, and now degree of v plus degree of w will be 9 plus 9, 18, which will be greater than equal to n, as n is greater than equal to 18. So Ohm's theorem then says this only: for every pair of distinct non-adjacent vertices v and w, if degree of v plus degree of w is greater than equal to n, then G is Hamiltonian. And we have just shown that for every non-vertices here, non-adjacent vertices here, degree of v plus degree of w is greater than equal to n. Indeed. So k9 comma 9 is Hamiltonian. I hope it's clear to you guys. So like, if none of the options A, B, C are correct, each of these, like we want to answer whether any of these is not Hamiltonian, but we actually showed that all of these are Hamiltonian. So answer is none of the above. Option D is. So is this clear, guys? This last part was a bit more involved. It was not too complex, but it was a bit too involved. So if you guys, you can take a look at it again later, or if you guys have any doubt right now, you can ask in chat. So let's move on to this question. So this question is just a straightforward application of something which we have already learned in lecture. So just want to remind you guys about this formula. So let E be the number of edges, V be the number of nodes, and R be the number of regions of a planar graph. We already know what a planar graph which can be embedded in a plane. Then which of the following inequalities holds true? So you guys can answer this directly, like you guys must have attended the lectures, right? So maybe you guys can try to answer this in chat. Which of the following formula is correct? Uh, this formula, one of these formulas has been discussed in the lectures. So if you have attended the lectures, you can just answer this straight away. Okay, maybe I'll just write the correct answer. So this is the inequality which is uh, correct. So 3r is less than equals to 2e. So I'll just leave this for you guys to figure out how is this true. Like it has already been in the lecture. So east side, I'll just write down the correct answer because it's just the lecture. So now let's come to question 9. Again, repetition of maybe previous session's problem, or remember if I uh, covered this in previous session, but this was also discussed in the lecture. So every graph has an odd number of odd degree vertices. Is this statement true or false? I think this is something which you call, this is related to something which was handshaking lemma. So guys, are you all asleep? I'm not a, none of you is writing anything in the chat right now. So yeah, Aditya is awake at least. So yeah, Aditya has written that this statement is false. So yeah, so this statement is false, that every graph has odd number of odd degree vertices. I think I have discussed the same question with you guys earlier also, but let's just go with it. So false. False, since every graph has an even number of odd degree vertices. Yeah. Okay. Another true false question. So this is maybe a bit interesting. So a bipartite graph can have an odd cycle. Is this true or is it false? So can a bipartite graph? So yeah, again Aditya has answered that this statement is false. So yeah, Aditya. These are just straightforward. These true false questions are straightforward. Just to remind you guys about the content of the lecture. So this statement is false. So if you guys remember, like a bipartite graph cannot can uh, a bipartite graph can only have even cycles. And what was the proof of that? Like once you go from left to right side, then you will have to come back from right to left side for a cycle. So you'll have to take even number of steps for making a cycle in a bipartite graph. So that's how this claim can be proven easily. So all cycles are of even length in a bipartite graph. But too difficult. So let's come to 11th question then. Okay, maybe I'll just put the whole question in the next page. So, okay, last two problems. Yeah, the last two problems. So which of the following graphs is self-complementary? Okay, another. I think this was a bit interesting question. So, uh, which of the following graphs do you think is self-complementary? So, self-complementary graphs are graphs like basically. Maybe I'll just write down. Let me think to remind you guys. Self-complementary graph. It's a graph which is isomorphic to its complement. So what were isomorphic graphs? Isomorphic graphs are graphs which have same structure but just different labeling. And a complement of a graph was just a graph which contains the edges which the original graph does not contain. Right? So it contains a complement set of the edges. So now a self-complementary graph is then a graph which is like complementary to like basically which is isomorphic to its own complement. So I hope the definition of self-complementary is clear. So a graph which is isomorphic to its complement. So now let's just test option by option which of the following graphs can be complementary, which of the following won't. So option A is C6. First of all, one thing to note is that isomorphic graphs will always have same number of edges, right? Since the graphs are identical, just the labeling is different, so number of edges can't be different for isomorphic graphs. So to prove that two graphs are not isomorphic, you can just say that if they're like one argument is that if two graphs have different number of edges, then they can't be isomorphic. So I hope that the statement I made is clear to you. So maybe we can just use that to show which of the following graphs are not self-complementary. So let's say C6, and we need to. So let's say the option is C6. So will it be self-complementary or it will not be self-complementary? To see this, we can just see that C6 has 6 edges, and so its complementary graph. So its complementary graph. What we need to show is that we take the C6, then we'll take the complement of C6, and I'll just try to show you that they have different number of edges. So yeah, Aditya, what you have written is correct. I'll just type it down for others also. So its complementary graph will have, let's say, 6C2 minus 6. So with this 6, so C6 has 6 edges. So C6 is just a cycle on 6 vertices, so it will have 6 edges. So its complementary graph will have basically 6C2 minus 6 edges, and this will come out to 6 into 5, which is 9 edges. Right. Since number of edges are different in complement, C6 cannot be self-complementary. So so basically what I shown is that so if the complement has different number of edges itself, then it can't be isomorphic to original graph. So if it is not isomorphic, then it is not self-complementary. So like note that by no means is this also like sufficient condition. Like two graphs cannot be isomorphic even if there can be a case where two graphs are not isomorphic even if they have same number of edges. So just checking the number of edges is not sufficient to say two graphs are isomorphic. But if the number of edges is not equal, then you can definitely say that they are not isomorphic. I hope you guys are getting the drift of what I'm saying. So now let's come to option B. So option B is P4. So P4 is just a path graph on 4 vertices, right? So let's just check by this edge argument only whether this edge argument will be satisfied or not. So P4 will be having 3 edges since it's a path on 4 vertices. So it will have 3 edges. So its complement will have 4C2 minus 3, which is again 3 edges. So at least we are able to see that we cannot rule out its self-complementariness using the number of edges argument. Now what I'm actually going to show is that it is complementary, it is self-complementary, and I'll just share a diagram with you guys. I'll just be sharing. Yeah. So let's just take the blue graph to be the original graph and this red graph to be the complementary graph. So as can be seen, this is P4, like this blue graph is P4, and this red graph will again form P4 only, right guys? Because the labeling of vertices can be different. Like here, the path goes from this vertex to this vertex, then to this, then to this. But the structure of the graphs is again similar. Like here also, it's a path graph. It's a P4 graph, like path graph on 4 vertices. This graph is also path graph on 4 vertices. Just the labeling of vertices will be different. So blue denotes original graph and red denotes the complementary. Both both graphs are P4, just pass graphs on 4 vertices. This to this, this to this, this to this. So indeed, option B is self-complementary. So now let's just come to option C. So option C is here P5. So again, we can use here number of edges argument to rule out that it is not self-complementary. How we can show it? P5 has 4 edges, right? Maybe I'll just copy paste all of this stuff and I'll just change the calculation. So its complementary graph will have basically, since it is P5, so it will have 5C2 minus 4 edges, which will come out to 5 times 4, 10 minus 4, which is 6. I hope my calculation is clear. So P5 had 4 edges, and so its complementary will have like total number of edges will be 5C2, and this had 4 edges, so its complementary will have 5C2 minus 4, which will evaluate to 6. So number of edges in complement. So number of edges in original graph was 4 and complementary was 6. So it cannot be self-complementary. So option C is not self-complementary. So option D was none of the above. It won't be correct since we had option B as self-complementary. Right. So option C is correct. So I hope you guys can see this easily using the diagram which I use for people. The original graph is using the blue edges and the dotted graph, or the red graph is the complementary graph, and both are like isomorphic. Okay, so last question for the day. So it is related to Euler's identity. Euler's. So if G is a 3 regular connected simple planar graph with 18 vertices, then the number of regions in G are. So will you guys like to try this out? It's a straightforward question. Just maybe I'll just make you guys aware of the Euler's identity. If it was for, I think it was for Euler's identity only. It says that let's say the number of regions is R and the number of vertices is V, then this is equals to like R plus V is equals to E plus 2, where E is the number of edges. So it says for any planar graph, R is number of regions, V is number of vertices, E is number of edges, then R plus V will be equals to E plus 2. For any connected, simple, planar. Yeah. The graph should also be connected as well as simple. In that case, this statement holds. And we are given that the graph is connected, simple, and planar. So one thing we can see is that we can use this Euler's identity maybe to find out the, like we have to find the number of regions. So we can use this Euler's identity maybe. So we have to find this R, and we have been given this V. This V we have been given as 18. But what about this E? The number of edges in the graph has not been given. So would any of you, like Aditya or Kushi? So do you see like how can you find this number of edges of this graph? Like it is only given that the number of vertices is 18. So can you find the number of edges in this graph? Okay, maybe I'll just complete the clip. So some properties what we have already used are connected, simple, as well as planar, and we also know there are 18 vertices. One thing which we are ignoring till now is that G is a 3 regular graph. So what is a 3 regular, let's say any D regular graph? D regular graph is, I think this definition has also been already covered in the lectures, is a graph which in which vertices in which all the vertices have degree of D. So here it's a 3 regular graph. So every vertex of G has a degree of 3 here. I hope I'm making sense, guys. So since G is 3 regular, every vertex of G has degree 3. And we already know that sum of degrees, this has already been covered in lecture, that sum of degrees of all vertices is equal to 2 times number of edges. Right guys, so from this equation maybe we can find this value of E, which we did not know. So sum of degrees of all vertices, since there are 18 vertices and all the each of those has degree 3, so this will just sum of degrees of all vertices will just be equals to 18 times 3, and this is equal to 2 times number of edges. So this implies that we get like 54 is equal to 2 times number of edges. From this we get number of edges is equal to 18 times 3 divided by 2, which is 27. So now we can use this theorem. We now know like planar, like we know V is equals to 18. We also have obtained E equals 27, and we need to find the value of R. So plugging in E equals 18 comma E equals 27 in Euler's identity, what we get is like this: R plus this V was 18, so R plus 18 is equals to E of 27 plus 2. So this gives R to be like, this will be 29 and this will be 18. 29 minus 18 is 11, so we get R equals 11. So this is our answer. We need to find the number of regions. The number of regions is equals to 11 in this question. So this sort of question is also present in your assignment, this week's assignment. So it will involve similar sort of principles as I have used here. So I believe you guys will be able to do that sort of question also. So yeah, guys, that's it for the day. So thanks for joining, and I think your assignment submission is tomorrow. So all the best for the assignment submission. So hopefully you enjoyed the session today, and we'll be meeting again next Tuesday, 6 to 8. So yeah, so we'll meet you guys next time around. I'll just stop the recording and then you guys can leave. Okay. Thanks guys. Bye bye.